The Andromeda Galaxy, a neighbor in the cosmic landscape. Our Milky Way is not alone in the vastness of the universe. We are in a local cosmic community known as the local group, a cluster of over 50 galaxies held together by gravity. Among these, our nearest large neighbor is the Andromeda Galaxy, a majestic spiral galaxy similar to our own. But what's fascinating about Andromeda is not just its size and beauty, but the fact that it is on a collision course with the Milky Way. In this introductory chapter, we will explore the fundamental features of the Andromeda Galaxy, its structure, and how it was discovered. Andromeda is much more than a distant object of interest. It is our future, deeply intertwined with the fate of the Milky Way. Andromeda, also known as Messier 31, M31, is the largest galaxy in our local group. It lies about 2.5 million light-years away from us, making it the most distant object visible to the naked eye. On a clear, dark night, it appears as a faint, elongated spot in the constellation Andromeda. The discovery of Andromeda as a galaxy separate from our own galaxy was a milestone in the history of astronomy. For centuries, astronomers referred to it as the Andromeda Nebula, believing it to be a gas cloud within the Milky Way. This changed in the early 20th century when Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. In 1923, Hubble used the Hooker telescope at Mount Wilson Observatory to observe stars in Andromeda. In particular, he identified a type of variable star known as a Cepheid variable, which allows astronomers to measure distances based on the relationship between a star's intrinsic brightness and its periodic fluctuations in brightness. Hubble's observations revealed that Andromeda was far too distant to be part of the Milky Way, confirming that it was a separate galaxy. This discovery forever changed our understanding of the cosmos and revealed that the universe is filled with countless galaxies. The Andromeda Galaxy is massive, about twice the size of the Milky Way, with a diameter of approximately 220,000 light-years. It is estimated to contain over 1 trillion stars, more than the Milky Way's estimated 200 to 400 billion stars. Like the Milky Way, Andromeda is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars from which spiral arms extend outward. These spiral arms are filled with gas, dust, and young hot stars, giving the galaxy its characteristic bright, glowing appearance. The structure of Andromeda is divided into several important components. At the heart of Andromeda lies a densely packed region of older stars known as the galactic bulge. This bulge is much larger than that of the Milky Way, and is dominated by stars that formed billions of years ago, shortly after the galaxy's initial formation. The central bulge also hosts a supermassive black hole, similar to the one at the center of our galaxy. Andromeda's spiral arms are regions of continuous star formation. Here, huge clouds of gas and dust collapse under gravity to form new stars, giving the galaxy its dynamic and vibrant character. The spiral arms also host numerous HII regions, areas of ionized hydrogen gas that shine brightly in visible light and mark sites of recent star births. The galaxy's disk is surrounded by a massive halo of stars and dark matter. The halo contains hundreds of globular clusters, spherical collections of stars that orbit the galaxy's core. Some of these globular clusters are among the oldest objects in the universe, dating back nearly 13 billion years. Although the stars and gas in Andromeda are visible through telescopes, they make up only a small fraction of the galaxy's total mass. Like many galaxies, Andromeda's rotation and structure suggest the presence of a vast amount of invisible material known as dark matter. In fact, dark matter is thought to make up about 90% of the galaxy's total mass. Dark matter cannot be observed directly because it does not emit, absorb, or reflect light. However, their gravitational effect on visible matter, such as stars and gas, allows astronomers to infer their presence. Without dark matter, the stars in Andromeda's outer regions wouldn't rotate as quickly as they do. This mysterious form of matter plays a crucial role in shaping the structure and dynamics of the galaxy. The exact nature of dark matter remains one of the greatest mysteries in modern astrophysics. Scientists have proposed several candidates for what dark matter could be, including weakly interacting massive particles, WIMPs, or axions, but no direct evidence has yet been provided. Like the Milky Way, Andromeda is not alone in the cosmic wilderness. It is surrounded by a collection of smaller satellite galaxies that orbit it, similar to how moons orbit a planet. The most notable satellite galaxies include Messier 32, M32, Messier 110, M110, and several dwarf galaxies such as NGC 205 and NGC 147. These satellite galaxies are gravitationally bound to Andromeda and interact with it in complex ways. Over time, some of these smaller galaxies are torn apart by Andromeda's tidal forces and absorbed into the larger galaxy, contributing to its growth. This process of galactic cannibalism is a common feature of galaxy evolution, as larger galaxies devour smaller ones. In fact, there is evidence that Andromeda has absorbed several smaller galaxies in the past. Traces of these previous mergers can be seen in the form of stellar streams, the elongated structures of stars left behind by destroyed dwarf galaxies. These currents provide valuable clues to Andromeda's history and her role as a cosmic predator. Although Andromeda is currently 2.5 million light-years away, it is not drifting into the distance. In fact, it is moving towards the Milky Way at a speed of about 110 kilometers per second. This means that in about 4 to 5 billion years, the two galaxies will collide in a spectacular cosmic event. The collision between Andromeda and the Milky Way, often called the Milkomeda event, will result in the merger of the two galaxies into a single, larger, elliptical galaxy. Despite the massive scale of this collision, it is unlikely that individual stars would collide because the space between stars is vast. However, the gravitational interactions between the galaxies will dramatically change their structure, hurling stars and gas clouds across space and triggering new waves of star formation. In the long term, this merger will reshape the local group, with Andromeda and the Milky Way forming the core of a new, larger galactic system. The fate of Earth and our solar system during this collision is uncertain. Although the planets could be thrown into new orbits, they are likely to survive the event. However, by this time the Sun will have already become a red giant, making Earth uninhabitable long before the galaxies merge. As we reflect on the inevitability of this future collision, we begin to appreciate the dynamic and ever-changing nature of the universe. Andromeda may seem far away now, but its fate is closely linked to that of the Milky Way. This cosmic dance between galaxies reminds us of the forces that have shaped the universe over billions of years and makes us ponder what lies beyond the distant future of our cosmic neighborhood. The anatomy of Andromeda, a closer look at its galactic structure. Andromeda, our galactic neighbor, is not just an ordinary spiral galaxy. It is a cosmic masterpiece with unique structural elements that astronomers have been studying for decades. Its spiral arms, halo, bulge, and core tell the story of a dynamic, ever-evolving galaxy. In this chapter, we take a detailed journey through the various layers of Andromeda, from the luminous center to the outermost reaches of its halo. At the heart of Andromeda lies a supermassive black hole. This black hole is estimated to have a mass of about 100 million times the mass of our Sun. This is more than 10 times as massive as the Milky Way's central black hole, Sagittarius, a star. The existence of a supermassive black hole at the center of galaxies like Andromeda is not uncommon. In fact, most large galaxies are believed to harbor such objects in their cores. The black hole is located in a dense region of older stars, known as the galactic bulge. This central bulge is much larger and more pronounced in Andromeda than in the Milky Way, extending thousands of light years from the center of the galaxy. The stars in this bulge are predominantly old and metal-rich, having formed billions of years ago during Andromeda's early history. The supermassive black hole and surrounding bulge are also home to fascinating astronomical phenomena, such as X-rays, which are produced when gas is heated as it falls into the black hole. These emissions are a telltale sign of activity in the galactic center, although the black hole is not as active as in some other galaxies, such as quasars. In a quasar, material falling into the black hole produces intense radiation, but Andromeda's black hole is relatively quiet in comparison, only occasionally flaring up as it engulfs passing clouds of gas. Beyond the central bulge lie Andromeda's magnificent spiral arms, home to some of the galaxy's most dramatic processes. These arms are the most striking feature of spiral galaxies like Andromeda and are home to many of the galaxy's youngest stars. Andromeda's spiral arms are dense regions of gas and dust that provide the raw material for star formation. When gas clouds in these arms collapse under gravity, new stars are formed, often in clusters. Some of these newborn stars are massive and shine brightly, quickly using up their fuel before ending their lives in violent supernova explosions. These explosions, in turn, enrich the surrounding regions with heavy elements and seed future generations of stars and planets. The rate of star formation in Andromeda has varied throughout its history. Today, the galaxy is thought to be forming stars at a slower rate than in the past, producing about 1 solar mass of new stars per year. For comparison, the Milky Way forms about 1.5 solar masses of stars annually, but both galaxies are relatively quiet compared to some starburst galaxies, which can produce stars hundreds of times faster. Andromeda's spiral arms are also home to vast HII regions, clouds of ionized hydrogen gas that shine brightly in the visible spectrum. These regions are illuminated by intense ultraviolet radiation from nearby young hot stars. Some of our galaxy's most famous nebulae, such as the Orion Nebula, have counterparts in the spiral arms of Andromeda and serve as birthplaces for future stars. A particularly famous HII region in Andromeda is NGC 604, one of the largest star-forming regions in the galaxy. This massive nebula is more than 4 times the size of the Orion Nebula and is home to dozens of extremely massive stars. The energy from these stars shapes the surrounding gas, creating breathtaking structures that are visible even from Earth with powerful telescopes. Beyond Andromeda's bright star-filled disk lies its halo, a region composed mostly of dark matter and a sparse collection of stars. Dark matter plays a crucial role in the structure of galaxies. Although we cannot see or detect dark matter directly, its gravitational effects are clearly visible in the rotation curves of galaxies, including Andromeda. Without dark matter, Andromeda's outer stars wouldn't move as quickly as they do. Based on the visible mass of the galaxy, stars, gas, and dust, the outer stars should move significantly slower the further they get from the core. But observations show that they continue to orbit at surprisingly high speeds. This discrepancy is explained by the presence of dark matter, which extends far beyond the visible parts of the galaxy and accounts for the majority of Andromeda's mass. Dark matter forms a massive halo around the galaxy, enveloping both its stars and satellite galaxies. The halo of Andromeda is also home to the remnants of smaller galaxies that were swallowed up by Andromeda throughout its history. These remnants form star streams, long, thin bands of stars that stretch across the sky, tracing the orbits of dwarf galaxies torn apart by Andromeda's gravity. One of the best-known examples is the giant star stream, which is believed to be the remnants of a dwarf galaxy that was swallowed up by Andromeda several billion years ago. This process of galactic cannibalism is still underway, and Andromeda continues to interact with its satellite galaxies, gradually integrating them into its structure. Scattered throughout Andromeda's halo are globular clusters, dense collections of tens of thousands to millions of stars. These clusters are among the oldest objects in the universe, dating back almost 13 billion years. Studying these clusters provides valuable insights into the early history of Andromeda and the universe itself. Andromeda's dominance in the local group is evident from the dozens of smaller satellite galaxies that orbit it, much like the Milky Way has its own satellite galaxies, which include the Magellanic Clouds. Among Andromeda's most significant companions are Messier 32, M32, and Messier 110, M110, both dwarf elliptical galaxies that orbit Andromeda's disk relatively close. M32 is a strange galaxy. It is much smaller than Andromeda, but contains a dense core of stars, making it unusually bright for its size. Some astronomers believe that M32 was once a much larger galaxy, but was stripped of its outer stars and gas by interactions with Andromeda, leaving only its dense core. Supporting this hypothesis, M32 lacks the gas and dust typically found in spiral galaxies, suggesting that much of its material was lost in previous encounters. M110 is another dwarf elliptical galaxy, but unlike M32, it still contains some regions of star formation. It also hosts several globular clusters, suggesting that it has retained more of its original structure despite being close to Andromeda. M110 is in the process of tidal destruction by Andromeda, meaning it may eventually be integrated into the larger galaxy. In addition to these two main satellites, Andromeda is orbited by a large number of smaller dwarf galaxies that are difficult to observe due to their faintness. Some of these dwarf galaxies are far out in Andromeda's halo, while others are closer and may eventually be absorbed by the galaxy. Although Andromeda appears static from our position on Earth, it is constantly evolving. The galaxy's spiral arms continue to rotate, its stars form and die, and its satellite galaxies gradually merge with it. This evolution is driven by both internal processes, such as star formation and supernova explosions, and external factors, such as gravitational interactions with other galaxies. One of the most significant changes in Andromeda's future will be its collision with the Milky Way, as mentioned earlier. This collision will trigger massive changes in both galaxies and lead to the formation of a new elliptical galaxy that will look very different from Andromeda or the Milky Way as we know it today. Andromeda isn't just a distant neighbor, it is a changing galaxy, shaped by the same forces that govern the evolution of galaxies throughout the universe. From its supermassive black hole to its dark matter halo, Andromeda offers a glimpse into the processes that will shape the future of the Milky Way and the universe itself. As we move beyond Andromeda's structure and delve deeper into its history and future interactions with the Milky Way, we will see how these two galaxies are destined to collide and merge, creating one of the most spectacular events in the history of the cosmos. Galactic collision course: the future encounter of Andromeda and the Milky Way. Astronomers estimate that the collision between Andromeda and the Milky Way will occur in about 4 to 5 billion years. Although that may seem like an unimaginably long time, on a cosmic scale it is a relatively short moment. By understanding the motions of both galaxies, astronomers were able to model the details of this impending event with remarkable precision. Galactic collisions are not uncommon in the universe. They are a common and natural part of galaxy evolution. When galaxies collide, it's not as catastrophic as it might sound. Because of the enormous distances between individual stars, it's unlikely that stars or planetary systems will actually collide. Instead, the galaxies will interpenetrate each other, their shapes being distorted by gravitational forces, their gas clouds interacting to form new regions of star formation, and their stars being thrown into new orbits. The most significant effect of a galactic collision is the gravitational interaction between the two galaxies. As Andromeda and the Milky Way get closer, their gravitational forces begin to distort their shapes. The spiral arms of both galaxies are pulled apart and stretched out into long streams of stars, gas, and dust called tidal tails. This collision will also trigger a burst of star formation. As galaxies' gas clouds collide and compress, they form new stars at an accelerated rate. This process, known as a starburst, will produce clusters of bright young stars that illuminate the remnants of colliding galaxies. Some of these stars will be massive and end their lives in violent supernova explosions, enriching the surrounding regions with heavy elements. After the first collision, Andromeda and the Milky Way will continue to orbit each other, gradually losing energy through the interactions of their stars and dark matter halos. Over the course of several billion years, the two galaxies will eventually merge into a single larger galaxy. This new galaxy will likely be an elliptical galaxy, unlike spiral galaxies like Andromeda and the Milky Way. Elliptical galaxies are typically more spherical in shape and do not have the prominent spiral arms characteristic of galaxies such as Andromeda and the Milky Way. This is because the collision disrupts the ordered orbits of stars in the spiral arms and randomizes their movements, resulting in a more even distribution of stars. One of the most fascinating questions surrounding the Milkomeda event is what will happen to our solar system. Although the merger of two giant galaxies may seem like a violent event, the large distances between the stars mean that the solar system is unlikely to be directly affected by collisions with other stars. Nevertheless, the position of the solar system within the galaxy will change dramatically. The solar system, currently located in the outer reaches of the Milky Way's disk, could be thrown into a completely different orbit within the new elliptical galaxy by gravitational forces. Depending on how the gravitational forces play out, the solar system could end up much closer to the galactic center or be thrown further out into the outer regions of the merged galaxy. By the time the Milky Way and Andromeda collide, the Sun will be nearing the end of its life. In about 5 billion years, the Sun will have exhausted its supply of hydrogen and will begin to expand into a red giant. This transformation will make Earth uninhabitable long before the galactic merger is complete. Nevertheless, this cosmic drama will continue to unfold, regardless of whether there is still life in the solar system or not. Dark matter plays a crucial role in the collision between Andromeda and the Milky Way. Although dark matter is invisible and does not interact with light, it has mass and exerts gravitational forces on galaxies. Both Andromeda and the Milky Way are surrounded by massive dark matter halos that will influence the dynamics of the collision. As the two galaxies get closer, their dark matter halos begin to interact with each other long before the stars and gas clouds. The dark matter halos are much larger than the visible parts of the galaxies and extend well beyond the edges of the spiral arms. These halos affect the orbits of the stars and gas within the galaxies, slowing them down and helping to bring the galaxies together. Dark matter will also play a role in the final merger of the two galaxies. As the galaxies interact, their stars will lose energy, and the dark matter will help stabilize the new merged galaxy. The distribution of dark matter in the new elliptical galaxy will determine its final shape and structure. Even though we can't directly observe the future collision of Andromeda and the Milky Way, astronomers have created detailed simulations to model how this event might play out. Using data from observations of both galaxies, and applying the laws of physics and gravitational dynamics, these simulations allow scientists to view the collision in a virtual environment and glimpse the future of our galactic neighborhood. One of the best-known simulations of the Milky Way event was created by NASA's Hubble Space Telescope team, which used data from Hubble observations to simulate the collision. The simulation shows how the two galaxies approach each other, interpenetrate each other, and ultimately merge into a single elliptical galaxy over the course of several billion years. These simulations are not only fascinating to watch, but also provide valuable insights into the physics of galactic collisions. By studying similar mergers in other parts of the universe, astronomers can refine their models and improve our understanding of how galaxies evolve through interactions. While the upcoming collision between Andromeda and the Milky Way represents a significant event for our local group, galaxy collisions are common throughout the universe. Many of the most massive galaxies we observe today, including the elliptical galaxies and galaxy clusters, are the product of previous mergers of smaller galaxies. One of the best-known examples of a galaxy collision are the antennae galaxies, NGC 4038 and NGC 4039. A pair of interacting galaxies located approximately 45 million light-years away. These galaxies are in the process of merging, and their tidal tails, long streams of stars and gas, are some of the most spectacular features in the night sky. The antenna galaxies offer a glimpse of what the Milky Way and Andromeda might look like during their own merger. On an even larger scale, galaxy collisions contribute to the formation of the cosmic web, the large-scale structure of the universe. Galaxies are not isolated entities, but rather part of vast networks of filaments, clusters, and voids. The interactions between galaxies, driven by dark matter and gravity, help shape these cosmic structures over billions of years. As we look at the collision between Andromeda and the Milky Way, we are reminded that our place in the universe is not static. Galaxies are constantly evolving, merging and changing, driven by the fundamental forces of gravity and dark matter. Although the Milky Way event is still billions of years in the future, it is just one step in the ongoing process of galactic evolution that has shaped the universe since its formation. As we delve deeper into the future of our galactic neighborhood, we will explore how the collision of Andromeda and the Milky Way fits into the larger story of the local group and the ultimate fate of the universe itself. The local group, Andromeda, Milky Way, and their galactic companions. As we continue to unravel the story of Andromeda's future collision with the Milky Way, it is important to consider the bigger picture of this impending galactic merger. The Milky Way and Andromeda are not isolated entities drifting through the cosmos. They are part of a gravitationally bound collection of galaxies known as the local group. Understanding the dynamics of this group is key to understanding the significance of the Andromeda-Milky Way collision and its implications for the future of our galactic neighborhood. In this chapter, we will examine the structure and composition of the local group, examine the role of smaller satellite galaxies, and explore how the interactions between its members have shaped and will continue to shape the future of this galactic family. What is the local group? The local group is a collection of more than 50 galaxies that are gravitationally connected and span a space of about 10 million light-years. This cosmic family is dominated by three major galaxies: Andromeda, the Milky Way, and the Triangular Galaxy, Messier 33 or M33. These three spiral galaxies make up most of the stellar mass in the local group, while the remaining members are smaller dwarf galaxies. Although the local group is relatively small compared to massive galaxy clusters like the Virgo cluster, it plays a crucial role in the cosmic environment around us. The gravitational interactions between its members are responsible for shaping the future orbits and eventual mergers of the galaxies within this group. Our home galaxy, the Milky Way, is a barred spiral galaxy containing between 200 and 400 billion stars. It stretches about 100,000 light-years across and is home to the solar system, as well as countless other star systems, nebula, and star clusters. The Milky Way's disk is divided into several spiral arms, and its central thickening region contains a supermassive black hole known as the Sagittarius A star. While the Milky Way is one of the dominant members of the local group, its fate is inextricably linked to Andromeda, the largest galaxy in the group. As previously mentioned, the Milky Way and Andromeda are on a collision course, and their eventual merger will permanently alter the structure of the local group. The largest galaxy in the local group, Andromeda, is a barred spiral galaxy, about 220,000 light-years across, making it more than twice the size of the Milky Way. Andromeda contains an estimated 1 trillion stars and has a well-defined structure with prominent spiral arms, a large central thickening region, and an extended halo of stars and dark matter. Andromeda's role as the gravitational anchor of the local group is significant because its mass and proximity to the Milky Way determine the dynamics of the entire group. The upcoming merger of Andromeda and the Milky Way will mark the beginning of a new era for the local group. The Triangular Galaxy, also known as Messier 33, M33, is the third largest galaxy in the local group. It is a smaller spiral galaxy about 60,000 light-years across, about half the size of the Milky Way. Despite its smaller size, M33 is an important member of the local group and has its own satellite galaxies and star-forming regions. The future of M33 is uncertain. Some simulations suggest that M33 may merge with Andromeda before the collision with the Milky Way occurs, while others suggest that it will be catapulted into a more distant orbit around the newly formed elliptical galaxy formed by the merger of Andromeda and the Milky Way. Either way, M33 will play a role in the future dynamics of the local group. Beyond the three large galaxies, the local group is populated by dozens of smaller galaxies, many of which are dwarf galaxies. These smaller galaxies are gravitationally bound to the larger galaxies and often orbit them as satellites. Over time, some of these dwarf galaxies may be drawn into and merge with the larger galaxies, allowing stars and gas to contribute to their growth. The Milky Way is orbited by two prominent dwarf galaxies, known as the Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC. These irregular galaxies are visible from Earth's southern hemisphere and are among the closest galaxies to the Milky Way. The LMC is about 163,000 light-years away, while the SMC is about 200,000 light-years away. The Magellanic Clouds are currently interacting with the Milky Way, and their fate will most likely be to be drawn into our galaxy. The interaction between the Magellanic Clouds and the Milky Way has already resulted in the formation of a stream of gases and stars, known as the Magellanic Stream, which extends over more than 100,000 light-years and envelops the Milky Way. Andromeda is also home to a collection of satellite galaxies, including Messier 32, M32, Messier 110, M110, and a number of smaller dwarf galaxies such as NGC 147 and NGC 185. These satellites are gradually being drawn to Andromeda and are likely to merge with the larger galaxy in the future. The fate of these satellite galaxies is similar to that of the Magellanic Clouds. They will either merge with their host galaxy or be torn apart by gravitational forces, contributing to the growth of Andromeda's stellar halo. In addition to the prominent satellites of the Milky Way and Andromeda, the local group is home to numerous other dwarf galaxies, many of which are faint and difficult to observe. These galaxies include Leo I, Leo II, Fornax, and Carina, among others. These dwarf galaxies are important for studying galaxy formation and evolution in general because they provide insights into the role of dark matter in galaxy formation and the processes that control interactions between galaxies. Some of these dwarfs may eventually be captured by the larger local group galaxies, further contributing to the ongoing process of galactic growth and merger. Dark matter is an essential component of the local group, as well as all galaxies. While the visible stars and gases in the local group galaxies make up only a small fraction of their total mass, the majority of the mass consists of dark matter. This invisible substance exerts gravitational forces that influence the movements of the galaxies, stars, and gases within the group. The presence of dark matter in the local group helps explain why galaxies remain gravitationally bound, despite the expanding universe. Without dark matter, the galaxies would likely drift apart, but the gravitational pull of dark matter holds the local group together. The dark matter halos surrounding the Milky Way, Andromeda, and other galaxies are much larger than the visible parts of these galaxies and extend far into intergalactic space. As the galaxies in the local group interact and eventually merge, dark matter will play a significant role in determining the dynamics of these mergers. The dark matter halos of Andromeda and the Milky Way are already interacting, although the visible parts of the galaxies have not yet collided. These halos will form the final structure of the new galaxy formed by the merger. The future of the local group will be dominated by the impending merger of its two largest members, Andromeda and the Milky Way. This event will mark the beginning of a new phase in the evolution of the local group, as the two galaxies will merge into a single, larger elliptical galaxy. The triangular galaxy, M33, could also play a role in this merger, either by merging with Andromeda before the Milky Way or by being captured later by the new elliptical galaxy. After the merger of Andromeda and the Milky Way, the resulting galaxy will be known as Milkomeda, a giant elliptical galaxy that will dominate the local group. The formation of this new galaxy will take billions of years, with stars being scattered into new orbits, tidal tails stretching across space, and new star-forming activity lighting up the cosmic stage. As Milky forms, the smaller local group galaxies, such as M33 and the dwarf galaxies, will either be absorbed into the new galaxy or remain in orbit around it. Over time, gravitational interactions will likely cause these smaller galaxies to merge with Milky, further contributing to its growth. The local group is part of a larger cosmic structure known as the local supercluster, which includes other galaxy groups and clusters, such as the Virgo cluster. While the local group is currently gravitationally bound, it will eventually merge with other nearby groups of galaxies as part of the ongoing cosmic evolutionary process. The local group is not an isolated system, but part of the cosmic web, the vast network of galaxies, dark matter and gas that permeates the universe. This web is made up of interconnected filaments, clusters, and voids, with galaxies such as Andromeda and the Milky Way forming the bright spots in this vast structure. As the local group evolves, it will continue to interact with the surrounding cosmic web, attracting matter from neighboring regions and contributing to the continued growth of the universe. The merger of Andromeda and the Milky Way is just one chapter in the story of cosmic evolution, a process that will continue for billions of years, long after the Milky Galaxy formed. In the next chapter, we will delve deeper into the mechanics of galactic evolution and examine how galaxies like Andromeda and the Milky Way form, grow, and interact with the surrounding cosmic environment. Galactic evolution, the life cycle of galaxies such as Andromeda and the Milky Way. Galaxies, much like living organisms, are born, evolve, and eventually fade away. Their life cycles span billions of years and are shaped by a variety of processes, including star formation, mergers, and interactions with other galaxies and dark matter. In this chapter, we will examine the stages of galactic evolution, focusing on how galaxies like Andromeda and the Milky Way have evolved over time and what their future will be. Understanding the life cycle of galaxies gives us insights into the long-term dynamics of the universe and how galaxies, including those in the local group, grow and change over cosmic time. Galaxies first formed shortly after the Big Bang, which occurred approximately 13.8 billion years ago. In the early universe, the cosmos was a hot, dense plasma of particles and radiation that gradually cooled and expanded over time. As the universe cooled, hydrogen and helium atoms began to form, and slight fluctuations in density caused by quantum fluctuations during the Big Bang allowed matter to clump together under the influence of gravity. After the Big Bang, the universe entered a phase known as the Cosmic Dark Age, which lasted about a few 100 million years. During this time, stars had not yet formed and the universe was dark, with only neutral hydrogen and helium gas filling the vacuum. As gravity pulled these gas clouds together, the first stars and galaxies began to form. These early galaxies were small and irregularly shaped, lacking the structure and complexity of modern spiral and elliptical galaxies. These early star-forming regions emitted light for the first time, ending the dark ages of the universe in a process known as reionization. The first galaxies were much smaller than modern galaxies like Andromeda and the Milky Way, containing only a few million stars compared to the hundreds of billions we see today. Over time, these small galaxies merged and interacted with each other, forming the larger structures that populate the universe today. One of the main drivers of galactic evolution is the process of galactic merger. As galaxies interact and collide with one another, they grow in size and complexity, forming new stars and changing shapes. Mergers play a crucial role in the formation of spiral galaxies such as Andromeda and the Milky Way, as well as larger elliptical galaxies. The current theory of galaxy formation is known as hierarchical formation, which states that large galaxies form through the gradual merging of smaller galaxies. In this process, small galaxies merge into larger ones, allowing the formation of the spiral and elliptical galaxies we see today. Both Andromeda and the Milky Way grew through this process, absorbing smaller galaxies throughout their history. Larger galaxies often devour smaller galaxies in a process known as galactic cannibalism. This process continues today, as Andromeda and the Milky Way continue to attract and absorb dwarf galaxies from their surroundings. The evidence of previous mergers is visible in the streams of stars left behind by these smaller galaxies, which have been stretched and scattered by the gravitational forces of the larger galaxy. In the case of Andromeda, several satellite galaxies have already been gobbled up, and their remnants can be observed as faint streams of stars in the galaxy's halo. The Milky Way is also currently absorbing the Sagittarius dwarf galaxy, which has left behind a similar stream of stars. In addition to merging with other galaxies, galaxies such as Andromeda and the Milky Way grow through the accretion of gas from the intergalactic medium. This gas provides the raw material for the formation of new stars and allows galaxies to renew their stellar populations over time. The process of gas accretion explains how galaxies can maintain their star-forming regions even after billions of years of evolution. Star formation is one of the key factors driving the evolution of galaxies. The rate at which a galaxy forms new stars, known as its star formation rate, determines its structure, brightness, and the types of stars that populate it. During their life cycle, galaxies go through different phases of star formation, depending on their environment and interactions with other galaxies. Spiral galaxies, such as Andromeda and the Milky Way, are known for their active star-forming regions, particularly in their spiral arms. These regions contain large clouds of gas and dust, known as molecular clouds, that collapse under gravity and form new stars. Massive stars that form in these regions burn brightly and die quickly in supernova explosions, while smaller stars like the Sun burn more slowly and persist for billions of years. Some galaxies go through periods of intense star formation known as starburst activity, during which their star formation rate increases dramatically. This can happen after a galactic merger or interaction when the gas in the galaxies is compressed, triggering the formation of large numbers of new stars. Starburst galaxies shine brightly due to the presence of massive, short-lived stars, but quickly deplete their gas supplies, leading to a decline in star formation. Elliptical galaxies, often formed by the merger of two spiral galaxies, have a much lower star formation rate compared to spiral galaxies. This is because much of the gas in elliptical galaxies has been consumed or heated during the merger process, preventing new stars from forming. Over time, the stars in elliptical galaxies get older, and the galaxy becomes dominated by older, redder stars. This decline in star formation marks the final phase of galactic evolution, as the galaxy evolves from an active, star-forming galaxy to a quieter one. As Andromeda and the Milky Way approach their eventual merger, both galaxies are already in the later stages of their evolution. While they still have active star-forming regions, their overall star formation rates are much lower than in the past. This decline is a natural part of galactic aging, as gas supplies for new star formation gradually dwindle. Andromeda is still actively forming stars, particularly in its spiral arms and HII regions, but its star formation rate is lower than that of the Milky Way. Some studies suggest that Andromeda's star formation rate could continue to decline as the galaxy ages and absorbs its remaining satellite galaxies. The Milky Way is also in a phase of slower star formation compared to its peak billions of years ago. However, it still contains significant star-forming regions, such as the Orion Arm and the galactic center. The future collision with Andromeda is expected to trigger a new wave of star formation as the gas clouds of both galaxies collide and become compressed. The collision between Andromeda and the Milky Way will not only change the structure of both galaxies, but also affect their star formation rates. As the gas in the two galaxies interacts, new stars are formed in a brief period of starburst activity. However, once the gas is exhausted, the newly formed elliptical galaxy, Milky, will likely go through a long period of little or no star formation, similar to other elliptical galaxies. Dark matter plays an essential role in the evolution of galaxies, even if we cannot observe it directly. Dark matter makes up most of the mass in galaxies and is the gravitational framework that holds galaxies together. Without dark matter, galaxies like Andromeda and the Milky Way would not have enough mass to explain the movements of their stars and gas. Galaxies are embedded in vast halos of dark matter that extend far beyond the visible parts of the galaxy. These halos stabilize galaxies and protect them from being torn apart by gravitational interactions with other galaxies. Dark matter halos are also involved in the process of gas accretion, as they create deep gravitational wells that pull gas from the intergalactic medium into the galaxy. During the upcoming merger of Andromeda and the Milky Way, the dark matter halos of both galaxies will play a crucial role in determining the dynamics of the collision. The dark matter will help absorb the energy of the interacting stars and gas, allowing the galaxies to merge more smoothly. The final structure of the resulting elliptical galaxy is shaped by the distribution of dark matter in the halos of the original galaxies. The life cycle of galaxies like Andromeda and the Milky Way is part of a much larger cosmic cycle that has been occurring since the beginning of the universe. Galaxies form from the primordial gas left behind after the Big Bang, grow through mergers and interactions, and eventually decay as they use up their star-forming material. Over time, galaxies will continue to interact, merge, and evolve, forming new structures and driving the ongoing evolution of the universe. The story of Andromeda and the Milky Way is just one chapter in this cosmic saga. As we look to the future and consider the impending merger and formation of Milky Way, we are reminded that galaxies are not static objects, but dynamic, ever-changing systems. Their life cycles are shaped by the forces of gravity, dark matter, and star formation, which together create the breathtaking diversity of galaxies we see in the universe today. The role of black holes in galactic evolution, the dark hearts of Andromeda and the Milky Way. A supermassive black hole lurks at the center of almost every large galaxy, including Andromeda and the Milky Way. These gigantic invisible gravitational engines have a profound impact on the evolution of galaxies, influencing everything from star formation to the distribution of gas and stars within the galaxy. In this chapter, we will examine the role that black holes play in shaping the structure and fate of galaxies such as Andromeda and the Milky Way. Supermassive black holes are among the most enigmatic objects in the universe, and their influence extends far beyond their immediate surroundings. Despite their invisibility, their presence is felt throughout the galaxy as they alter the dynamics of gas, stars, and dark matter. By studying the black holes at the center of Andromeda and the Milky Way, astronomers are gaining valuable insight into the hidden forces that drive galactic evolution. The center of the Andromeda Galaxy hosts a supermassive black hole similar to the Milky Way. This black hole, known as M31, pronounced M31 star, has a mass about 100 million times the mass of our Sun, making it significantly larger than the Milky Way's central black hole, Sagittarius A star. The existence of a supermassive black hole at the center of Andromeda was first suspected by astronomers through observations of the movements of stars near the galaxy's core. Using the Hubble Space Telescope, astronomers were able to track the speeds of the stars orbiting the center of the galaxy. The stars in the central region were found to be moving at incredibly high speeds that could not be explained by the mass of the visible stars alone. This suggested the presence of an enormous, invisible mass, later identified as a supermassive black hole. Although M31 is currently relatively quiet, it likely played an important role in shaping the galaxy over its lifetime. In the past, this black hole may have been more active, accreting gas and material from its surroundings. During these periods of activity, M would have emitted 31 powerful beams of energy, potentially affecting the distribution of gas and stars in the central regions of the galaxy. Supermassive black holes can undergo periods of intense activity known as active galactic nuclei, AGN. During these phases, the black hole devours large amounts of gas and dust and emits enormous amounts of radiation. Although Andromeda's black hole is currently in a quiet phase, it could become active again in the future, especially during the galaxy's merger with the Milky Way. At the heart of the Milky Way is Sagittarius A star, Esger A, a supermassive black hole with a mass about 4 million times the mass of the Sun. Although it is smaller than the black hole in Andromeda, Sagittarius A has been the subject of intense study due to its proximity to Earth and the fact that we can observe it more easily than black holes in other galaxies. Sagittarius A is located approximately 26,000 light-years from Earth at the center of the Milky Way's galactic bulge. Despite its relative proximity on astronomical scales, it is difficult to observe directly because it is surrounded by dense clouds of gas and dust. However, astronomers have studied SCIR-A by tracking the movements of stars near the galactic center. In the year 2022, astronomers made a breakthrough when they observed the star S2 orbiting Sagittarius A at incredibly high speeds. By carefully tracking S2's orbit, scientists were able to confirm the presence of a supermassive black hole at the center of the Milky Way. This work gained international recognition and helped solidify our understanding of black holes and galaxies. Like Andromeda's black hole, Sagittarius A is currently in a relatively quiet state, meaning it is not actively devouring large amounts of material. However, there is evidence that Sagittarius A has experienced periods of intense activity in the past. Astronomers have detected X-rays and other forms of radiation near the galactic center, suggesting that the black hole occasionally devours material from its surroundings. In the distant future, when the Milky Way merges with Andromeda, Sagittarius A could become active again, engulfing gas and material disturbed by the merger. This could lead to the formation of powerful jets of radiation that influence the structure of the newly formed galaxy. When Andromeda and the Milky Way collide in the distant future, their central black holes will play a crucial role in shaping the outcome of the merger. As the two galaxies approach each other, their black holes will gradually converge and eventually merge into a single, even larger, supermassive black hole. This merger will release an enormous amount of energy in the form of gravitational waves, which will radiate outward as ripples in the space-time continuum. The merger of two supermassive black holes is one of the most powerful events in the universe. As the black holes move toward each other, they lose energy in the form of gravitational waves. These waves were predicted by Einstein's general theory of relativity, and their discovery is a major goal of modern astrophysics. In the year 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, confirming Einstein's predictions. Since then, several black hole mergers have been observed through their gravitational wave signals. The merger of the black holes in Andromeda and the Milky Way will produce one of the strongest gravitational wave signals ever produced, although this will occur long after the end of human civilization. After the two galaxies merge, the black holes at their centers will also merge into a single supermassive black hole. This new black hole will likely be even larger than M31, with a mass over 100 million times the mass of the Sun. The newly formed elliptical galaxy, Milky Way, will be dominated by this massive black hole at its center. Supermassive black holes don't just sit passively at the centers of galaxies. They actively influence the evolution of their host galaxies through a process known as black hole feedback. Black hole feedback occurs when the energy emitted by an active black hole affects the gas and stars in the surrounding galaxy, regulating star formation and shaping the structure of the galaxy. During periods of intense activity, supermassive black holes can produce active galactic nuclei, AGN, which are extremely bright regions around the black hole. AGN are powered by the accretion of gas and material onto the black hole, which heats up and emits large amounts of radiation. This radiation can drive powerful gas outflows that push material out of the galaxy's center and suppress star formation. In some cases, feedback from black holes can even cause galaxies to completely shut down their star-forming regions, resulting in the formation of red and dead galaxies that contain older stars and have little or no ongoing star formation. This process is considered a key factor in the evolution of elliptical galaxies, which often have very low star formation rates. As Andromeda and the Milky Way merge, the activity level of M31 is likely to increase. The disruption caused by the collision will direct gas toward the black hole, providing it with the fuel it needs to enter an AGN phase. This could lead to powerful outflows of gas that will influence the evolution of the newly formed galaxy. Likewise, Sagittarius A could become more active as the Milky Way merges with Andromeda. Black hole activity could suppress star formation in the central regions of the new galaxy and influence the final structure of Milkomeda. However, the exact timing and outcome of this process remains uncertain and depends on the amount of gas available during the merger. Black holes are often viewed as cosmic destroyers, but they also play a key role in the long-term evolution of galaxies. Supermassive black holes such as M31 and Sagittarius A are expected to remain at the centers of their galaxies for billions of years, continuing to influence the movements of stars and gas. In the distant future, as the universe continues to expand and galaxies drift further apart, black holes may be among the last remaining objects in the universe. As stars burn out and galaxies fade, black holes will continue to exist and eventually release their energy through what is known as Hawking radiation, a theoretical process predicted by physicist Stephen Hawking. Although this process occurs over timescales far beyond human comprehension, the ultimate fate of supermassive black holes is to gradually evaporate, leaving behind only the faintest remnants of their former great power. As we explore the role of black holes in shaping the future of galaxies like Andromeda and the Milky Way, we are reminded that these enigmatic objects are at the center of the evolution of the universe itself. In the next chapter, we will look at the cosmic web and examine how galaxies like Andromeda fit into the larger structure of the universe. The cosmic web, Andromeda's place in the larger universe. Galaxies like Andromeda and the Milky Way are not isolated islands in space. Instead, they are part of a complicated cosmic network that stretches across the entire universe, known as the cosmic web. This vast web consists of filaments of galaxies, clusters, and dark matter connected by invisible threads spanning billions of light years. Understanding the structure and dynamics of the cosmic web helps us view Andromeda and the Milky Way in the context of the larger universe and reveals how galaxies evolve at the largest scales. In this chapter, we will examine the structure of the cosmic web, how it came to be, and what role Andromeda plays in this gigantic structure. We'll also look at how galaxies like Andromeda interact with their cosmic environment and the role dark matter plays in shaping the universe as we know it. The cosmic web is the largest structure in the universe, a network of interconnected filaments and voids that stretches across the entire observable universe. It is made up of galaxies, galaxy clusters, and dark matter, all held together by gravity. The cosmic web is not evenly distributed. While some regions are densely filled with galaxies and clusters, there are other vast, empty regions where very little matter exists. The filaments that make up the cosmic web are vast strands of galaxies and dark matter that stretch across hundreds of millions of light years. These filaments are the result of gravity pulling matter together in the early universe. Over time, these structures grew and formed the backbone of the large-scale structure of the universe. Galaxies like Andromeda and the Milky Way are small points of light within these filaments, orbiting clusters of galaxies and traveling through the dark matter web. Between the filaments of the cosmic web are vast empty regions known as voids. These voids are sparsely populated with galaxies and are among the most isolated places in the universe. The largest voids, so-called supervoids, can measure hundreds of millions of light years across. These voids form when gravity pulls matter from less dense regions, leaving cosmic deserts behind. At the intersections of filaments in the cosmic web are massive galaxy clusters containing hundreds or even thousands of galaxies held together by gravity. These clusters are some of the most massive objects in the universe, with total masses up to a quadrillion times the mass of the Sun. Galaxy clusters play a crucial role in shaping the cosmic web, as their immense gravitational force attracts galaxies and dark matter from the surrounding filaments. The cosmic web is the result of billions of years of cosmic evolution, shaped by the gravitational force acting on matter after the Big Bang. To understand how the cosmic web came into being, we must look back to the very early universe and the seeds of structure formation. Shortly after the Big Bang, the universe was a hot, dense plasma of particles and radiation. As the universe expanded and cooled, it reached a point where the first atoms could form and light could travel freely through space. This light, known as the cosmic background radiation, CMB, provides a picture of the universe when it was only about 380,000 years old. Small fluctuations in the density of matter in the early universe, visible in the CMB, provided the seeds for the formation of galaxies and the cosmic web. These small superdensities, created by quantum fluctuations in the early universe, were amplified by gravity over billions of years, eventually forming the large-scale structure we see today. Dark matter played a crucial role in the formation of the cosmic web. Although it does not emit, absorb, or interact with light, dark matter makes up about 85% of the total mass of the universe. Their gravitational pull helped bring together ordinary matter to form the first galaxies and clusters. Without dark matter, the universe would not have formed the intricate web of structures we see today. As the universe expanded, dark matter clumped together under the influence of gravity, forming the first dark matter halos. These halos attracted gas, which cooled and collapsed to form the first stars and galaxies. Over time, these early structures merged together, creating the larger filaments and clusters that make up the cosmic web today. Andromeda, the Milky Way, and the rest of the local group are part of a much larger cosmic structure known as the local supercluster, or Laniakea supercluster. This supercluster contains tens of thousands of galaxies and spans more than 500 million light-years. The local group, which includes Andromeda and the Milky Way, is part of the Laniakea supercluster, a vast collection of galaxies and galaxy clusters. Laniakea is one of many superclusters that make up the cosmic web, and it is dominated by the Virgo cluster, a massive cluster of galaxies located approximately 53 million light-years away. The name Laniakea means immense paradise in Hawaiian and reflects the vastness of this structure. The Virgo cluster, the largest and most massive galaxy cluster in Laniakea, contains over 2,000 galaxies and has a total mass about 100 times that of the local group. While the Milky Way and Andromeda are significant galaxies within the local group, they are relatively small compared to the massive clusters of galaxies that dominate the local supercluster. However, their gravitational interaction will contribute to the ongoing evolution of the cosmic web, as the merger of Andromeda and the Milky Way will eventually add mass to the larger structures within the supercluster. After the merger, the newly formed Milky Galaxy will continue to travel through the cosmic web, interacting with other galaxies and clusters over the course of billions of years. While the local group is currently relatively isolated, it is slowly drifting toward the Virgo cluster, and in the distant future, it could become part of this vast structure. As the universe continues to expand, the cosmic web will continue to evolve. Galaxy clusters and superclusters are growing larger as gravity pulls more and more matter into these dense regions. However, the expansion of the universe driven by dark energy will ultimately cause distant galaxies to drift beyond the observable universe, leaving behind isolated clusters and superclusters. In the distant future, billions or even trillions of years from now, galaxies like Andromeda and the Milky Way will be part of isolated superclusters, cut off from the rest of the universe. This process, known as cosmic isolation, will leave behind small clusters of galaxies surrounded by vast, empty spaces. Dark matter is key to understanding the structure of the cosmic web. Although we cannot see dark matter, its gravitational influence shapes the distribution of galaxies and clusters in the universe. Without dark matter, the cosmic web as we know it would not exist. Every galaxy, including Andromeda and the Milky Way, is embedded in a giant dark matter halo. These halos are invisible, but they contain most of the galaxy's mass. Dark matter provides the gravitational glue that holds galaxies together and prevents them from flying apart as they rotate. The formation of dark matter halos was a crucial step in the evolution of the cosmic web. In the early universe, dark matter clumped together to form small halos, which then attracted gas and formed the first stars and galaxies. Over time, these halos merged together, forming the larger structures we see today. One of the most powerful tools for exploring the cosmic web is the use of cosmological simulations. These simulations use supercomputers to model the evolution of the universe, starting with the Big Bang and continuing through billions of years of cosmic history. One of the most well-known simulations of the cosmic web is the Millennium simulation, which tracked the formation of galaxies, clusters, and dark matter over time. By comparing these simulations with real observations of the universe, astronomers can better understand how the cosmic web formed and evolved. The Virgo cluster is the dominant structure in the local supercluster and lies approximately 53 million light-years away. It contains over 2,000 galaxies and is one of the largest galaxy clusters in the universe. The Virgo cluster's gravity is so strong that it affects the motion of galaxies far beyond its immediate surroundings, including galaxies in the local group. Both Andromeda and the Milky Way are slowly drifting toward the Virgo cluster, drawn by its powerful gravitational pull. This movement is part of a larger flow of galaxies within the local supercluster as gravity pulls them toward the densest regions of the cosmic web. Just as individual galaxies can merge, clusters of galaxies can also collide and merge over time. When two galaxy clusters merge, an even more massive structure is formed, with hundreds or thousands of galaxies orbiting within a single massive dark matter halo. These mergers are among the most energetic events in the universe, releasing enormous amounts of energy in the form of X-rays and gravitational waves. In the distant future, the local group may eventually merge with the Virgo cluster, contributing to the continued growth of the cosmic web. As Andromeda travels through the cosmic web, its interactions with other galaxies and clusters will shape its future. While the galaxy is currently part of the local group, its ultimate fate is tied to the larger structures of the universe, including the Virgo cluster and the local supercluster. The upcoming merger between Andromeda and the Milky Way will be a significant event in the evolution of the local group. After the merger, the newly formed Andromeda Galaxy will continue to travel through the cosmic web, interacting with other galaxies and clusters over the course of billions of years. Over the next billion years, the local group will continue to evolve as galaxies merge and interact as part of the larger cosmic web. While Andromeda and the Milky Way are now the dominant members of the local group, their merger will produce a new galaxy that will eventually be absorbed into larger structures such as the Virgo cluster. The story of Andromeda is not just the story of a single galaxy. It is part of a much larger cosmic dance shaped by the forces of gravity and dark matter. As we look into the future, Andromeda's journey through the cosmic web will continue to reveal new insights into the structure and evolution of the universe. Andromeda and exoplanets. The search for worlds beyond our solar system. While our focus on the Andromeda Galaxy so far has been primarily on its structure, evolution, and impending collision with the Milky Way, there is another equally fascinating aspect to consider: exoplanets. Exoplanets, i.e. planets that orbit stars outside our solar system, are one of the most exciting areas of modern astronomy. Although we have already discovered thousands of exoplanets in the Milky Way, the idea that there could be exoplanets in Andromeda takes the fascination of planet hunting to a whole new cosmic level. In this chapter, we will explore the possibilities of exoplanets in Andromeda, the challenges of discovering such planets over such vast distances, and what these distant worlds might tell us about planet formation, habitability, and the potential for life elsewhere in the universe. Although we have not yet confirmed any exoplanets in Andromeda, the tools and techniques we have developed for exploring planets in our own galaxy open a window into the possibilities of also finding planets in our neighboring galaxy. Before we turn to the potential exoplanets in Andromeda, it is important to understand the history of exoplanet discovery in our own galaxy. The first confirmed discovery of an exoplanet occurred in 1992, when astronomers discovered planets orbiting a pulsar, a highly magnetized, rotating neutron star. However, it took until 1995 for the first exoplanet to be confirmed around a Sun-like star, Pegasi b. Since then, the search for exoplanets has exploded, thanks to the development of new observation techniques and the launch of dedicated space missions, such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. These missions have allowed astronomers to discover exoplanets by observing the dimming of a star's light as a planet passes in front of it, known as the transit method, or by detecting the slight wobble of a star caused by the gravitational attraction of an orbiting planet, known as the radial velocity method. To date, astronomers have confirmed the existence of over 5,000 exoplanets in the Milky Way, with many more planets still awaiting confirmation. These planets vary widely in size, composition, and orbital characteristics, from hot Jupiters, gas giants that orbit very close to their stars, to Earth-like planets located in the habitable zones of their stars, where conditions may be suitable for liquid water to exist. One of the most surprising discoveries in exoplanet research is the sheer diversity of planetary systems. While our solar system has a relatively orderly arrangement of rocky planets near the Sun and gas giants further out, many exoplanet systems are far more chaotic. In some systems, massive gas giants orbit closer to their stars than Mercury does to the Sun, while others host multiple planets in tight, compact orbits. The concept of the habitable zone is crucial when searching for potentially habitable exoplanets. The habitable zone is the area around a star where conditions could allow liquid water to exist on a planet's surface. Although the presence of liquid water is not a guarantee of life, it is considered one of the main ingredients for life as we know it. Many exoplanet searches focus on finding planets within the habitable zones of their stars, as these are considered the most likely candidates to support life. Could Andromeda host exoplanets? Given the incredible diversity of exoplanets in the Milky Way, it is extremely likely that Andromeda also hosts a huge number of exoplanets. Andromeda is about twice the size of the Milky Way and contains about 1 trillion stars compared to the Milky Way's estimated 200 to 400 billion stars. With so many stars, the likelihood that Andromeda hosts exoplanets, perhaps even more than the Milky Way, is extremely high. Similar to the Milky Way, Andromeda has stars ranging from young, hot stars in the spiral arms to older, cooler stars in the galaxy's central bulge. These stars likely host planetary systems similar to those we see in our own galaxy. If planet formation is a universal process, then it is reasonable to assume that Andromeda contains planets of all kinds, Earth-like rocky worlds, gas giants, ice giants, and perhaps even exotic planets that we have not yet discovered. While the discovery of exoplanets in the Milky Way is now relatively common, finding exoplanets in Andromeda presents significant challenges. The biggest difficulty is the immense distance. Andromeda is about 2.5 million light-years from Earth. At this distance, standard techniques for detecting exoplanets, such as the transit method and radial velocity measurements, are extremely difficult to use. In the Milky Way, the discovery of exoplanets is based on observing tiny changes in a star's brightness or movement. But at Andromeda's distance, individual stars are much dimmer and harder to resolve, making it difficult to detect the tiny signals from orbiting planets. Additionally, the sheer number of stars in Andromeda complicates the search, as it becomes increasingly difficult to distinguish one star's signal from another. Although discovering exoplanets in Andromeda remains a challenge, advances in telescope technology may soon make it possible. Future space telescopes, such as the James Webb Space Telescope, JWST, and the proposed LUVOIR, Large UV Optical Infrared Surveyor, are designed to observe distant objects with unprecedented precision. These instruments could potentially be used to observe exoplanets in nearby galaxies like Andromeda directly, or through the use of gravitational microlensing, a technique that takes advantage of the bending of light by a massive object to reveal distant planets. If we could discover and study exoplanets in Andromeda, it would be a unique opportunity to compare planetary systems in different galaxies. While the Milky Way and Andromeda are similar in size and structure, they have different histories and environments, which could lead to differences in the types of planets they host and the way planetary systems evolve. Studying exoplanets in Andromeda would allow astronomers to test whether the same processes that control planet formation in the Milky Way also apply in other galaxies. For example, we could compare the abundance of different types of planets, such as gas giants and rocky planets in Andromeda, with that in the Milky Way. We could also study how the chemical composition of stars in Andromeda influences the types of planets that form around them. If Andromeda has a higher or lower abundance of certain planet types compared to the Milky Way, it could provide important clues about how the galaxy's unique environment influences planet formation. For example, Andromeda's slightly higher star formation rate could lead to differences in the distribution of planet types. One of the most exciting aspects of studying exoplanets in Andromeda would be the search for habitable worlds. Although detecting signs of life from such a great distance would be a daunting challenge, the first step would be to find planets within the habitable zones of stars in Andromeda. These planets could provide valuable insight into whether life-friendly conditions are widespread across the universe, or whether Earth is a rare exception. If we find evidence of habitable planets in Andromeda, it would raise the tantalizing possibility that life could exist outside our galaxy. Even though we don't yet have direct evidence of extraterrestrial life anywhere in the universe, the discovery of Earth-like planets in Andromeda would suggest that the ingredients for life could also be present in other galaxies. Life in Andromeda, if it exists, would be influenced by different cosmic and environmental factors than life in the Milky Way. For example, the different rates of star formation, supernova activity, and even the distribution of dark matter in Andromeda could influence the potential for life to emerge and evolve on distant planets. The search for exoplanets both in the Milky Way and beyond has just begun. As technology advances, astronomers hope to push the boundaries of exoplanet detection to discover not only planets in our own galaxy, but also those in neighboring galaxies like Andromeda. The James Webb Space Telescope, JWST, launched in 2021, is designed to observe distant objects in the infrared region of the spectrum. Its powerful optics and sensitivity will allow it to study the atmospheres of exoplanets in the Milky Way with unprecedented precision. Although its primary mission is to observe stars and galaxies within our galaxy, the JWST may also be able to detect exoplanets in nearby galaxies through direct imaging or other techniques. The LUVOIR mission, currently under consideration by NASA, would be one of the most powerful space telescopes ever built. With a large mirror and a wide range of capabilities, LUVOIR could potentially detect exoplanets in Andromeda and other neighboring galaxies through direct imaging. This would represent a major leap forward in our ability to study planets beyond the Milky Way. Another promising technique for discovering exoplanets in distant galaxies is the gravitational microlensing method. This method exploits the bending of light caused by the gravitational field of a massive object such as a star or planet. When a planet passes in front of a distant star, it can create a lensing effect that enhances the star's light and reveals the planet's presence. Although difficult to observe, this technique offers the potential to discover exoplanets in Andromeda and beyond. As we continue the search for exoplanets in the Milky Way and beyond, we face one of science's most profound questions. Are we alone in the universe? Although we have not yet found clear evidence of life beyond Earth, the discovery of exoplanets in Andromeda would be a major step forward in answering this question. The idea that there could be entire planetary systems in Andromeda that might even harbor life broadens our perspective on the universe. It reminds us that we are part of a vast, interconnected cosmos, full of possibilities yet to be explored. Andromeda, our closest galactic neighbor, may hold the answers to some of existence's greatest mysteries. Answers that could fundamentally change our understanding of life's place in the universe. Andromeda's past, the formation and evolution of the galaxy over billions of years. Understanding the Andromeda Galaxy's past offers insights into the processes that shaped not only our galactic neighbor, but also galaxies throughout the universe. Like the Milky Way, Andromeda began forming shortly after the Big Bang, and its long, complex history is marked by collisions, mergers, and the birth and death of countless stars. Andromeda's current structure is the result of billions of years of galactic evolution, driven by the same cosmic forces that govern the behavior of all galaxies. In this chapter, we will explore the formation of Andromeda, its early stages of development, and the major events that shaped it into the massive spiral galaxy we see today. We'll also look at the evidence astronomers use to piece together this cosmic history and how it reflects the broader history of galaxy evolution in the universe. The Andromeda Galaxy, like all galaxies, traces its origins to the earliest epochs of the universe. Shortly after the Big Bang, the universe was a hot, dense soup of particles and radiation. As it expanded and cooled, the first atoms formed, mainly hydrogen and helium. These primordial elements clumped together under the influence of gravity and formed the seeds of the first stars and galaxies. The seeds of Andromeda's formation were sown during a period of rapid expansion known as cosmic inflation, which occurred fractions of a second after the Big Bang. During this time, tiny fluctuations in the density of matter were stretched over vast distances, creating slight variations in the distribution of matter throughout the universe. These fluctuations in density provided the gravitational force necessary to pull matter together and form galaxies, including the early building blocks of Andromeda. Dark matter, an invisible substance that makes up most of the universe's mass, played a crucial role in the formation of galaxies. As the universe expanded, dark matter began to clump together, forming the first dark matter halos. These halos acted as gravity wells that attracted gas and formed the first stars and galaxies. Andromeda's dark matter halo began to form in the early universe, providing the framework for the galaxy's growth over the next billion years. The formation of the first stars in Andromeda marked the beginning of its transformation from a simple cloud of gas and dark matter into a luminous galaxy. These early stars, known as population 3 stars, were composed almost entirely of hydrogen and helium because heavier elements such as carbon, oxygen, and iron had not yet formed. Population 3 stars were massive, bright, and lived short, violent lives before exploding as supernovae, supplying the galaxy with its first heavy elements. The earliest stars in Andromeda were incredibly massive, with some estimates reaching hundreds of solar masses. These stars formed when gas clouds within the dark matter halo collapsed under their own gravity, triggering nuclear fusion in their cores. Because these stars contained very few heavier elements, called metals in astronomy, they were extremely hot and short-lived, lasting only a few million years before exploding as supernovae. The explosions of population 3 stars created the first heavy elements in Andromeda, such as carbon, oxygen, and iron. These elements were scattered into the surrounding gas, enriching it and allowing the next generation of stars, known as population 2 stars, to form. Population 2 stars were less massive than their predecessors, but contained trace amounts of heavier elements, making them more similar to the stars we see today. When the first stars formed in Andromeda and other galaxies, they began to emit light, ending the cosmic dark ages. This initiated a period known as reionization. The ultraviolet radiation from these early stars ionized the surrounding hydrogen gas, allowing light to travel freely through space and ushering in the age of the first galaxies. Like most large galaxies, Andromeda's growth was fueled by a process known as hierarchical merger. Small galaxies and star clusters merged together to form larger structures. Over billions of years, Andromeda grew by swallowing smaller galaxies and integrating their stars and gas into its expanding disk. This process of galactic cannibalism is a key factor in galaxy formation and has shaped the structure of many of the largest galaxies in the universe. In its early history, Andromeda was likely much smaller than it is today, consisting of a small, irregular cluster of stars and gas. But as it interacted with other galaxies around it, it began to grow through mergers. These interactions caused gas to collapse into the center of the galaxy, forming new stars and creating the spiral structure we see today. Evidence of past mergers in Andromeda is visible in the form of star streams, long, thin star paths that are the remnants of smaller galaxies torn apart by Andromeda's gravity. One of the best-known examples is the giant star stream, which is thought to be the remnant of a dwarf galaxy that was absorbed by Andromeda several billion years ago. As Andromeda merged with smaller galaxies, it not only grew in size, but also developed an extensive stellar halo. This halo contains many of the stars that were torn away from the smaller galaxies during the merger process. Today, Andromeda's halo is much larger than the visible part of the galaxy, extending hundreds of thousands of light-years from its center. This halo also contains many globular clusters, dense collections of ancient stars that formed early in the galaxy's. Andromeda's spiral arms likely formed through interactions with other galaxies. These arms are regions of active star formation where gas is compressed as it passes through the spiral structure. The gravitational force of neighboring or satellite galaxies can trigger the formation of spiral arms by inducing density waves in the galaxy's disk. These density waves act like traffic jams, causing gas to accumulate and form new stars. At the center of the Andromeda Galaxy lies a supermassive black hole known as M31, pronounced M31 star. This black hole is among the most massive in the local galaxy cluster, with a mass of approximately 100 million times the mass of the Sun. The formation and growth of this black hole are closely linked to the overall evolution of the galaxy, and it has likely played a significant role in shaping the structure of Andromeda over billions of years. Supermassive black holes grow by accreting gas and material from their surroundings. In the early stages of Andromeda's evolution, M31 was probably much smaller than it is today, but as the galaxy grew through mergers and collisions, so did the black hole. During intense accretion periods, M31 would have emitted large amounts of energy, potentially influencing star formation in the surrounding regions. Active supermassive black holes, like M31, in its more active phases, can influence the growth of galaxies through a process known as feedback. When a black hole accretes gas, it can emit powerful jets of radiation and particles that heat the surrounding gas and prevent it from collapsing to form new stars. This feedback mechanism can regulate star formation in the galaxy and help maintain balance between gas and stars. Today, M31 is in a relatively quiet period, meaning that it is not actively accreting large amounts of material. However, it is possible that the black hole could become active again in the future, particularly during Andromeda's upcoming collision with the Milky Way. As the two galaxies merge, gas and stars will be injected into the center of the newly formed galaxy, which could provide fuel for the black hole to accrete and reignite its activity. After billions of years of mergers, collisions, and star formation, Andromeda has evolved into one of the largest spiral galaxies in the local galaxy cluster. Its current structure is characterized by a bright central bulge, well-defined spiral arms, and an extensive halo of stars and dark matter. The galaxy's mass is estimated to be about 1 trillion solar masses, making it about twice the size of the Milky Way. At the center of Andromeda is a dense galactic bulge that contains older stars that formed early in the galaxy's history. The bulge is much larger than that of the Milky Way and is thought to have been formed by the merger of smaller galaxies in the past. The stars in the bulge are predominantly old and metal-rich, reflecting the galaxy's long history of star formation and enrichment. Andromeda's spiral arms are sites of ongoing star formation, particularly in regions known as HII regions, where young, hot stars ionize the surrounding gas, causing it to glow. These regions are among the brightest and most active areas of the galaxy, producing new stars that will eventually contribute to Andromeda's continued growth. Andromeda's disk is surrounded by an extensive stellar halo containing both stars and globular clusters that were likely accredited during past mergers. This halo also contains large amounts of dark matter, which makes up the majority of the galaxy's mass. The dark matter halo extends far beyond the visible part of the galaxy and plays a crucial role in maintaining Andromeda's structure. As we think about the formation and evolution of Andromeda, we begin to see how the galaxy's past has shaped its present, and how its future is tied to the Milky Way. The billions of years of galactic interactions and star formation that created Andromeda are part of the larger story of galaxy evolution in the universe, a story that will continue to unfold as Andromeda heads toward its impending collision with the Milky Way. Andromeda's future, the Milky Galaxy, and the fate of the local group. Having explored Andromeda's past and present, it's now time to look into its cosmic future. The impending collision between the Andromeda Galaxy and the Milky Way will be one of the most dramatic events in the history of the local group. It will fundamentally reshape both galaxies and create an entirely new structure, the Milky Galaxy. This galactic merger is inevitable, but will take place over billions of years, marking a turning point not only for Andromeda and the Milky Way, but also for the entire local group of galaxies. In this chapter, we will examine the details of the impending collision between Andromeda and the Milky Way, the formation of the Milky Galaxy, and the long-term fate of the local group in the expanding universe. We will also address how these events fit into the larger context of cosmic evolution and what they reveal about the ultimate fate of galaxies in an ever-expanding universe. Andromeda and the Milky Way are currently on a collision course, moving toward each other at a speed of about 110 kilometers per second. Although that sounds fast, the two galaxies are still separated by a massive distance of about 2.5 million light-years. Despite this distance, gravity is inexorably pulling them closer together, and in about 4 to 5 billion years, the two galaxies will begin to collide. A key piece of evidence for Andromeda's impending collision with the Milky Way is the observation of its blue-shifted light. While most galaxies in the universe are moving away from us due to the expansion of space, Andromeda is one of the few galaxies moving towards the Milky Way. This blue shift occurs because Andromeda's light waves are compressed as it approaches, making the light appear bluer to observers on Earth. This motion was first discovered in the early 20th century by Vesto Melvin Slipher, an American astronomer who measured the Doppler shift of Andromeda's light and realized that the galaxy was moving toward us rather than moving away from us. This discovery laid the foundation for today's understanding of the impending collision between Andromeda and the Milky Way. Andromeda's movement toward the Milky Way is caused by the gravitational attraction between the two galaxies. Both galaxies are part of the local group, a gravitationally bound collection of galaxies that includes over 50 smaller satellite galaxies. The combined mass of the Milky Way and Andromeda dominates the local group, and their mutual gravitational attraction will ultimately lead to their collision. However, when Andromeda and the Milky Way collide, the event won't be as violent as one might think. Although the galaxies will pass through each other, direct star-to-star collisions are unlikely due to the enormous distances between each star. Instead, the collision will involve the merger of the galaxy's gas clouds, dark matter halos, and gravitational fields, causing dramatic changes in the structure and appearance of both galaxies. As the two galaxies get closer to each other, their gravitational forces will begin to distort their shapes. The spiral arms of both galaxies are drawn into long streams of stars, gas and dust known as tidal tails. These tails are a common feature of galaxy mergers and provide visible evidence of the gravitational interactions between the colliding galaxies. Tidal forces will also cause stars and gas to be thrown into new orbits, changing the internal structure of both galaxies. Some stars may even be ejected from the galaxies entirely, while others will be pulled into the central regions, fueling the growth of supermassive black holes. The collision will also trigger a burst of star formation as the gas clouds of both galaxies collide and become compressed. This process, known as a starburst, will lead to the creation of millions of new stars, many of which will be massive and short-lived. These new stars will shine brightly for millions of years before exploding as supernovae, enriching the surrounding regions with heavy elements. Starburst activity is a hallmark of galactic mergers and can dramatically increase the brightness of colliding galaxies. However, this phase of intense star formation will be relatively short-lived as the gas supply is quickly depleted in the process. Both Andromeda and the Milky Way host supermassive black holes at their centers, M31 in Andromeda and Sagittarius, a star in the Milky Way. As the galaxies merge, these black holes will gradually spiral toward each other and eventually merge into an even larger supermassive black hole. The merger of two supermassive black holes is one of the most energetic events in the universe, releasing powerful gravitational waves, ripples in the structure of space-time. These gravitational waves will propagate outward from the collision event, but they will be far too weak to affect the rest of the universe. The end result of the collision between Andromeda and the Milky Way will be the formation of a new galaxy, Milkomeda. This new galaxy will likely be an elliptical galaxy, rather than a spiral galaxy like its predecessors. The chaotic forces of the collision will disrupt the ordered spiral structure of both galaxies, creating a more spherical, less structured galaxy. Elliptical galaxies are common products of galaxy mergers. When two spiral galaxies collide, the stars within the galaxies are thrown into random orbits, obliterating the organized spiral shapes. The result is a smooth, elliptical shape that no longer has the characteristic arms of a spiral galaxy. Milky will likely resemble other large elliptical galaxies, such as Messier 87, M87, a giant elliptical galaxy in the Virgo cluster. One of the most intriguing questions surrounding the collision of Andromeda and the Milky Way concerns the fate of the solar system. While the collision will dramatically change the structure of both galaxies, the solar system is unlikely to be directly affected by stellar collisions. Still, the gravitational forces involved could push the solar system into a new orbit within the merged galaxy, perhaps further away from the galactic center or closer to it. When the collision occurs, the Sun will have already reached the late stages of its life cycle, expanding into a red giant and potentially engulfing the inner planets, including Earth. The fate of the solar system will therefore be shaped by the evolution of the Sun long before the completion of the merger of Andromeda and the Milky Way. After the merger, Milky will continue to evolve for billions of years. Because most of the gas has been used up during the starburst phase, the new galaxy will enter a quieter phase with little or no new star formation. The stars in Milky are getting older and redder, and the galaxy is increasingly dominated by older, cooler stars. Milky will continue to interact with other galaxies in the local group, possibly merging with additional satellite galaxies or even with the triangular galaxy, M33, another spiral galaxy in the local group. The collision between Andromeda and the Milky Way is not the only event that shapes the future of the local group. Over time, the smaller satellite galaxies orbiting Andromeda and the Milky Way will either be absorbed into Milky or remain in their orbit around the new galaxy. The local group itself is part of a larger cosmic structure, the local supercluster, also called the Laniakea supercluster, which includes the massive Virgo cluster of galaxies. The Virgo cluster, about 53 million light-years away, is the largest and most massive galaxy cluster in the local supercluster. Both the local group and the Virgo cluster are moving toward each other, attracted by the gravitational forces of the surrounding dark matter. In the distant future, Milky may eventually be drawn into the Virgo cluster and become part of this larger structure. This process could take hundreds of billions of years, but would mark the final phase of the local group's evolution. While the local group is currently gravitationally bound, the rest of the universe is expanding at an increasing rate due to dark energy. As a result, galaxies outside the local group are moving away from us at ever higher speeds. In the distant future, this expansion will cause galaxies beyond the local group to disappear from our field of view, beyond the observable universe. This process, known as cosmic isolation, will isolate the local group, and ultimately Milky from the rest of the universe. In time, Milky and the remnants of the local group will become the only visible galaxies in the sky, as the rest of the universe recedes into darkness. Trillions of years in the future, the stars in Milky will begin to burn out, leaving only faint white dwarfs, neutron stars, and black holes. The galaxy grows darker and colder as its stars die, and eventually even the black holes will be vaporized by Hawking radiation, leaving a dark, empty universe. Although this future is unimaginably distant, it reminds us that galaxies and the forces that shape the universe are fleeting. Andromeda's future, like that of all galaxies, is part of a larger cosmic cycle that has unfolded over billions of years and will continue to do so for billions more. The story of Andromeda's impending collision with the Milky Way is not just a tale of cosmic destruction, it is a testament to the dynamic, ever-changing nature of the universe. Galaxies are not static entities, but rather living, evolving systems that are constantly shaped by the forces of gravity, dark matter, and star formation. As we look to the future of Andromeda and the local group, we gain a deeper understanding of our place in the cosmos. The universe is vast, complex, and interconnected, with galaxies like Andromeda playing a key role in the larger cosmic web. While Andromeda's fate may seem distant, it reminds us that even the seemingly most stable structures in the universe are subject to change, driven by the same fundamental forces that govern the evolution of the stars, planets, and galaxies we observe today.